Hey everyone, and welcome back. Today we're going to be bringing up a very cool subject. And yes, the pun is intended. We'll be talking about glaciers and ice sheets. Glaciers and ice sheets are really fascinating because they act unlike all the other materials that we've been talking about. Ice, in some ways, acts like a fluid. In other ways, it acts like a rock. So let's go ahead and just jump right into this. Here we have right on the image in front of you a picture of a glacier. This is a really active glacier. Right now, you don't actually have the skills to be able to interpret what all this topography means, this really hummocky and a jagged structure up here on the top. But by the end of this lecture, you'll know exactly what that means, what it is that has the interest of these researchers that are down here looking at this glacier coming into this inlet. We see little tiny icebergs, so ultimately we'll also be talking about the origins of icebergs as well. So let's just jump right in. So glaciers are basically, a glacier is a thick mass of ice that forms over hundreds of thousands of years by the accumulation, compaction, and recrystallization of snow. We have to face a simple fact that ice is a mineral. It's a mineral like many other minerals. It's inorganic, it's naturally occurring, it has a definitive crystal structure, and it has a uniform chemical composition, H2O. Water is always H2O. So it's a crystal, and therefore it behaves like a crystal. And when we talk about compaction and recrystallization is something that should go through your mind when we talked about metamorphism. So in a lot of ways, it actually glaciers behave almost like metamorphic rocks do. And if you remember metamorphic rocks, they were present primarily in the mantle. And it's the mantle convection, right? The fact that the mantle is able to convect and flow that allows plate tectonics to happen. Well, it turns out that these metamorphic ices that exist in glaciers allow glaciers to flow just the same, almost like a river. So as a consequence, glaciers kind of bridge the gap between two different cycles. The hydrologic cycle, where water can be trapped in a glacier for many years, right? Water can be evaporated out of the oceans and deposited on the land. This is the reason why when we see periods of immense glaciation during ice ages, the sea levels tend to drop because the water is evaporated in the ocean but deposited in the land. In other words, it's taken out of the system. And then when it melts, of course, it goes into a river and returns back to the ocean, and the sea levels rise again. We'll be coming back to this concept by the end of this lecture. And of course, it plays a major role in the rock cycle. We talked about frost wedging when we're talking about weathering of rocks or erosion of rocks early in the beginning third of the course. The rock cycle, the frost wedging was an important part of breaking up rocks, but glaciers are that second part where it transports those rocks out to the harbors, to the rivers, and what have you. And we'll be showing you those depositional cycles as we go through. But before we can really delve into that, we need to get into what glaciers are, how they move, what their architecture is, and what their role is in the hydrologic cycle. Okay. Well, there's two general themes that we should be introducing right away. There are valley glaciers, which are glaciers that exist in valleys of mountainous areas, and they're called alpine glaciers because they were found in the Alps, or they were described in the Alps first. They just basically flow down the valley. This is a classic case of an alpine glacier. To give you an idea of how big this is, you'll notice that these are researchers, these are human beings, just almost little pinpricks down here on the lower left to show you how big this glacier is. Okay, and then there's ice sheets, and ice sheets exist on a larger scale than valley glaciers. They basically cover everything, and they don't move. That's the important thing about ice sheets, is they basically don't move. The edges might move and turn into glaciers, but the ice sheet itself stays put. It's an accumulation zone of ice. And the best examples of major ice sheets on planet Earth are in Greenland and Antarctica, which is to say near the North Pole and at the South Pole. And here we see the distribution of these ice sheets as they exist currently. So here's Greenland right here. Parts of northern Canada are also part of this ice sheet. We also see ice sheets up here at Spitsbergen and some of these peninsulas up here. This is the famous Kola Peninsula of Russia. These peninsulas up here, or these islands up here, are basically locked in ice sheets. And of course, here's Antarctica, the continent at the bottom of the bottom of the world, of the bottom of the Earth, the South Pole, that is, which we know the least about because it's covered in ice. It's got this massive ice sheet over it. And so when we look at a map of it, we realize that sure enough, here's Antarctica. There's volcanoes here, there's rocks there, but they basically have to poke out from the ice for us to actually see them and study them very effectively. So the ice sheets, the modern ice sheets, come from a period of time about 18,000 years ago. The ice sheets covered large portions of North America, Europe, and Siberia. Siberia is this zone over here. Europe, basically Scandinavia, and even down into France and the area north of the Alps. And then here in North America, it came down to as far as Iowa, and possibly right along in this zone here into the Ohio Valley. So over the past 2.6 million years, ice sheets have advanced and retreated multiple times. So, if we have this line, we know that Siberia used to have ice. That means that the ice up here, the ice sheet has expanded down into Asia and into Europe. And the same thing as these ice sheets expanding down into North America. And then they retreat. Currently, they're obviously in a period of retreat. Antarctica, that's less obvious because the continent is relatively small and it is situated right on the South Pole. So it's kind of permanently covered in ice. And we want to make sure that we get some differentiation between what we mean by, or what we mean by ice in the sense of a glacier versus ice that you would find, say, up in frozen ocean. So the two main ice sheets are Greenland and Antarctica. And the Arctic Ocean is covered with sea ice, not glacial ice. So basically the North Pole is a location right at the top of, or at the northernmost point of the Earth where everything is rotating around that North Pole. But there is no continent located at that position. And so when we go to the North Pole, you can in fact walk out of the North Pole and you can stick a flag in the ice and the whole thing. But the main thing that you need to recognize is that the North Pole is in fact located in a zone of sea ice. And so this is a bunch of fractured sea ice chunks. Some of them are about 40 feet long here, about 40 feet by 20 feet. You could probably walk on them. I wouldn't advise it, but you probably could. And some of them are probably quite large as you move out towards the bay over here. Sea ice is up to 4 meters thick. That's about 18 feet. That's about 15 feet. Whereas glaciers are hundreds to thousands of meters thick, right? So the sea ice just freezes that uppermost crust of the ocean, and then it insulates the rest of the ocean from that very cold Arctic environment. So you basically have water from about 4 meters down. In fact, some of the first people, or the first technology to reach the North Pole were submarines that would go to the North Pole and then rise up through the sea ice. The gentlemen would get out, because they were always male at the time, would get out, and then they would plant a flag, take a picture, and then put the flag back in the submarine and then take off again. Okay, so this is very different from glaciers. Glaciers, by contrast, form on land, right? It's not frozen ocean. It's forming on land. And Greenland in the northern hemisphere and Antarctica is in the southern hemisphere are the places where we see these glaciers form for the most part. We do, of course, find glaciers in other places, Alaska and what have you, but these are the main producers of glaciers. Ice flows out in all directions from one or more snow accumulation centers, basically from the ice sheets, right? You pile up the snow and it starts to flow out towards the side. It starts to bleed out on the edges. Okay, so here we see a really neat feature. This is something called an ice shelf. It's part of the ice sheet, the ice sheet that extends off of the continents. And some of these ice sheets can extend out even into the ocean. And Antarctica is a classic example of this. So the ice sheet that extends from the land out into the ocean is called an ice shelf. Along parts of Antarctica, glacial ice flows into the sea, creating ice shelves. In shallow water, the ice touches the bottom and is grounded. In deep water, the ice shelf floats. And this is a very large ice shelf right here. Very, very tall, very thick. And in this case, this is the second of these two options here. This is an ice shelf that is not touching the ground. It is in fact floating on the water. But it is still connected to the continent. As a matter of fact, I can do a quick drawing and show you exactly what I mean. Hold on real quick. Okay, so we're back. And what were we talking about? We're saying an ice shelf. Well, imagine island or a continent or whatever. Put it a seafloor. The continent will rise up, drop back down, and then of course everything leading up to this. So this is all land. Okay, let's go ahead and put in our ocean here. Off to the sides, and piled up on top of this land mass that is sticking up out of the ocean. So this is the ocean here. Same thing over here, just keep it straight. Okay. We have ice covering everything. And so we have this ice sheet that forms. The ice sheet tends to cover everything on the land in Antarctica, forms a nice flat layer. And then when it hits the water, it can extend out into the water and even be floating on top of it. And of course it also extends underwater. Probably something more like this is probably more accurate. Okay. And so here we see our ice sheet. And here are the shelves. This is a floating shelf. So I hope that kind of clarifies what we're talking about. And occasionally material breaks off here at the edge of the ice sheet, and that material floats off. You know, maybe it looks like this in the ocean. This is an event called calving. And this produces things called icebergs. And so typical of Antarctica and Greenland. So Antarctica, I'll just put Ant/green. You know what I'm talking about. This is where you find most of the production of icebergs from calving events, and a nice floating shelf. The best floating shelf in the world is in Antarctica, the Ross Ice Shelf, for example. All right, so let's go back to our slideshow. So you get the idea that, you know, there's water underneath the ice sheet here. There's water underneath the ice sheet here, but it could be floating here, and right here it's actually in contact with the land. This is where it's in shallow water. This is where it goes into deeper water. And this has an immense effect on the type of organisms that could live here. Okay, so anyways, that's enough of this. Let's go back to our slideshow. Okay, so back to our ice shelf. We can see where the calving events have created this nice cliff on this floating ice shelf here. And of course, this is intuitive, thickest on land, or thickest landward side, and thin on the seaward side, right? So in other words, as it moves towards the ocean, it tends to get thinner. Some ice shelves are unstable and start breaking apart, and the breakup of ice shelves are attributed to regional global warming. A lot of places we see this, where the ice shelves are actually breaking faster than the new ice can come in and replace it. So as a consequence, the ice shelves are breaking up and getting smaller over time. Okay, there are other types of glaciers too, right? So we talked about the two basic ones. There's ice caps cover some upland plateaus. The ice caps and ice sheets feed outlet glaciers, right? So basically the ice starts to bleed out, which are tongues of ice extending outward from the large masses. So, you can imagine there's an ice sheet somewhere uphill of these glaciers here. Piedmont glaciers form when one or more alpine glacier emerges from the valley and spreads out on a broad lobe. And so that's what these are here. This is a beautiful Piedmont glacier. These are coming into this valley here from higher areas. This is actually another glacial valley down below. We'll describe how you can determine that little later on. And in fact, these glaciers are so active that they're controlling the drainage. They're pushing the river along the edge here, right? The river probably originally came along this side, and now the river's forced all the way over here to try to get around these glaciers. Okay? These are really, really beautiful. So in order to understand what makes these things operate, we need to talk about the ice itself. What is it about the ice that allows these things to happen? And of course, we're going to have to resurrect some of the concepts we were talking about in metamorphic rocks. Um, excuse me. Glaciers form in areas where more snow falls in winter than melts during the summer. Okay, so that's where they form. So in order to get a glacier, you need to have a snowpack, something that builds up over time. In fact, the best place to do this is above something called the snow line. So snow above the snow line does not melt in the summer. So if you have a bunch of snow that falls on a mountain and then it goes to summertime, that snow is stored. It doesn't leave, right? If it's above the snow line. If it melts completely away, then the snow line is above the level of that mountain or in that region. So for example, the snow line in Antarctica is around Antarctica. Fortunately, Antarctica doesn't melt every single year and then repack every, and cycle around. It's full of ice year round. So glacial ice formation, here's the process here is you get a snowflake, right? And basically the snowflake falls onto the surface of the land or the surface of the ice. And basically it begins to undergo some changes. It originally looks like this. Granular snow, that powdery snow actually has an appearance under the microscope like this. And then you could actually pack it a little bit more, and it becomes something new, right? These open spaces here actually have air, or the ability for air to get in. That air is getting squeezed out, and you just wind up getting these little granules of ice called firn, okay? And the firn can then be compressed even further into glacier ice. And so this is the process that's being described right here. Snowflakes become smaller, thicker, and more spherical. Air is forced out, and snow is recrystallized into a much denser mass of small grains called firn. Okay, so that's what we're talking about. All right, so this is what glacial ice looks like under a microscope. So once the thickness of the ice and the snow exceed 50 meters, in other words, once you get the firn under that much pressure, 50 meters of depth, firn fuses into a solid mass of interlocking ice crystals, and we call that glacial ice. And this is what it looks like under a microscope. It's really, really beautiful. Here you can see that there's nice interlocking crystals, just as it describes above. But notice that there's no real location in here for air to reside. There might be an occasional air pocket, say right here, but for the most part, the air is squeezed out. Here appears to be another air pocket right here. But for the most part, the air appears to be mainly squeezed out of this particular sample. So it's dense, it's full of water, it's heavy, and it's hard, right? Basically, think of your typical ice that you might get out of a freezer, except it's at higher pressure. All right, and so those characteristics are going to determine how glaciers actually move. So it's pretty obvious when we're talking about mass wasting. We talked about how things would slide down a hillside as a coherent block, right? And the top of a landslide block moves pretty consistently with the bottom of it in these large landslides. In the case of glaciers, that's not necessarily the case. In glaciers, the whole thing does move. You get sliding along the bedrock here. So here's a whole glacier. By the way, this dashed line right here is that 50-meter limit right here. We'll come to this here in a moment and describe in detail what's going on there. So the whole glacier will slide from, say, this position to this position right here. And you'll notice that this is the entire amount of motion that is attributable to sliding. But the top of the glacier moves a lot more than that. And the reason why is there's something called internal flow. The bottom of the glacier only slides this far, and then essentially what's restricting it is friction with the bedrock. But as you move up into the glacier is ductile, right? It's able to flow. It has internal flow characteristics similar to the mantle of the Earth, right? And you can actually start to see that the top part of the glacier will move faster through internal flow than just the sliding alone will allow. Okay, so as a consequence, the internal portion of the glacier starts to literally shear as the top part moves faster than the bottom part, and so it's almost like a deck of cards being slid across. Above 50 meters, we find firn, and then we get up into snowpack, right? And the interesting thing about this zone here is because it's not ductile, it doesn't flow, it breaks. It's brittle, just like the crust of the Earth is brittle and creates earthquakes. The same thing is the truth here in glaciers. And so you get these large fractures that start to break along the upper 50 meters here. Okay. Along the ground, the entire mass slides along the ground as basal slip, and meltwater acts as a lubricant. So there's a meltwater that will be moving right along the bottom as well. Okay, so it's kind of like a river in some respects, and it's like a landslide. It's kind of a hybrid of the two, and we'll be coming into a discussion of why this is faster right here. But it's akin to the flow of a river, if you remember the lecture on surface flow of rivers and water. So here's one of those fractures I was talking about. So the upper meters of a glacier is brittle and called the zone of fracture. Crevices, or if you were from Canada or England or some of these other English-speaking countries, they would call them crevasses. They both mean the same thing. These crevasses are cracks in the ice, and they're present in the zone of fracture but are sealed off by plastic flow at depth. So here's a deep crevasse. Here's an explorer of some type. He's going across a bridge. He's looking down into this crevasse, which is probably about 50 meters deep. Below that, there's nice flow and everything comes together. You wouldn't want to fall into this crevasse, of course, because at the bottom here, it's hard metamorphic ice, right? Really, really, really hard material. And it could be very, very unpleasant to fall that distance just to hit basically an ice rock. We should also talk about how fast these things move. You know, like a river, glacial ice does not all move at the same rate, right? So in a river, remember, the fastest position was at the top and at the middle for the most part, as long as the river was going straight. Flow is fastest in the center of the glacier. So here's a glacier. The position where it's moving fastest is right here at the top. Glacial velocity ranges from extremely slow, millimeters per year, to several meters per day. Some glaciers exhibit extremely rapid movements called surges. In other words, they can come down to a zone at glacial speeds and then all of a sudden move very fast. 60 meters per day is considered very fast for a glacier. Here we see a glacier that began doing a surge. This is in Alaska in 1983. Began moving at 60 meters per day. And what happened is as it hit this open area, it began to surge out. And as a consequence, it broke itself up. And so here we see this crevassed, heavily crevassed surface due to this surge. And now, hopefully, if you remember the first slide we showed, suddenly you know what this is what gives rise to this kind of topography. This is, in fact, a glacial surge that's moving into a fjord. We'll talk about fjords here shortly. All right, get back to that. All right, so let's talk about where this, what are glaciers all about? What is their purpose? And it's really not that different than a river in a lot of ways. There's glacial zones, there's zones of accumulation. It's where the snow falls. And then there's zones of wastage, which is where the snow melts or the ice melts. So the zone of accumulation is the area where a glacier forms. It's located above the snow line, which means year-round there's snow. It doesn't melt off. The zone of wastage is below the snow line. You see melting and you see calving, which is the breaking off of large pieces of ice. So icebergs where the glacier has reached the sea. This is where we get our icebergs from. And so if our snow line is located right here, as they've put in this image, this means that down here we start finding the breakup and the melting of the glacier, but up above we find the deposition of the ice that creates it. So it's basically a continuous landslide, or it's a continuous ice slide, if you will, where the material is moving into this valley and then eventually melting at the bottom. And it feeds these really cool streams. We'll come to these in a minute. The glacial budget is controlled by a couple of things. So basically, the glacial budget is the balance or lack of balance between accumulation and loss of ice, right? So a very, very large glacier is going to have a large amount of ice coming in at the head, but very, very little melting occurring near the toe, or what we would call the zone of wastage. So loss of ice at the lower end of the glacier is called ablation, right? So ablation is basically where it melts. If accumulation exceeds loss, the glacial front advances, right? So if you have way more ice than you do melting, the glacier moves. It moves away, or it becomes larger and it advances. If ablation increases or accumulation decreases, the glacial front will retreat. And so here we see a glacier that at one time went all the way down into the valley. It's now ablating right here on the edge of this hillside right here. So this is an example of extreme ablation. All right, so now we've talked about what glaciers do and what their function is, which is to move ice from areas upslope to areas downslope. We need to talk about the effect that this process has on rocks. In other words, its role in the rock cycle. Glaciers are capable of great erosion and sediment transport, huge amounts of sediment transport. And they do it in a couple of ways. First, as a glacier flows over a bedrock, it loosens and lifts blocks in a process called plucking. So imagine, there's a big boulder sitting on the ground, and an ice sheet or a glacier, advances, and it'll wrap itself around that boulder, and over time, it'll actually grab that boulder and hold it. It'll hold it within the glacier, and it'll begin to move it. Okay, and then when eventually the glacier will melt, and it'll just drop that boulder in place. So that's one thing that it can do, is it can move, loosen and lift blocks that are completely unmovable in any other way. Even rivers can't move boulders in this way for very long distances anyway. Rocks in the glacier also act like sandpaper to smooth and polish a rock surface in a process called abrasion. So here we see a perfect example of glacial abrasion on a rock. There's a rock, this is from the Sierra Nevada of California. The glacier, when it came through this zone, polished that rock smooth so well that light reflects off of it. In fact, you probably, if you're unfortunate, you could even slip on this if it happens to be a wet surface. So, you get an idea. These things can get really, really, really flat. And the production of two things come from this. You get rock flour, which is pulverized rock. As you grind this stuff up, it winds up floating into the glacial ice. There's a myth out there that suggests that glacial ice is completely pure. It is in fact not. It's full of rock flour. Probably not the best thing to be drinking, even though I know a lot of tour companies try to sell people on the idea of drinking glacial ice. The other thing that it does is it leaves the abrasions themselves. It leaves glacial striations, which are the grooves in the bedrock. And if you look carefully, you can see that there's some straight lines in this polished surface right here. And that is in fact the glacial striations. Now, the amount of erosion is controlled by the rate of movement, the thickness of the ice, types of rock fragments trapped in the ice, it turns out, and of course the erodibility of the surface below the glacier. It's much easier to erode sands, loose sands and gravels than it is to erode granite. And that seems to be the main factors in control. And this results in some pretty cool landforms that you don't see anywhere else, right? You don't necessarily find these types of features outside of glaciated regions. So valley glaciers have this really cool feature. They flow down here, and here's another valley glacier flowing right here to the side. And as they go around this mountain on one side and on this side, what they do is they tend to erode the bottom of this mountain range right here in the front, right here. And so you have mountains that originally are like this, and then over time, they get steepened on the sides. And you wind up with really, really sharp ridges. You also get nice points. Here's another set of sharp ridges here. And this is what alpine glaciers tend to do, is to make very, very sharp points on our mountain peaks. Ice sheet topography tends to do the opposite. It tends to subdue the topography. It makes things kind of flat, a little more mundane. Here we can actually see nice flat surfaces. This was once covered by an ice sheet. So glacial valleys are the main mechanism by which glaciers move across the land surface. And the reason why is because they're so good at eroding things, right? That they dig their own valleys while they're moving. So as opposed to taking advantage of other things. Glaciers widen and deepen valleys, creating U-shaped glacial troughs. And here we see a nice, beautiful U-shaped valley right here. Glaciers tend to straighten valleys, removing sharp curves and creating truncated spurs. In the case of glaciers versus rivers, rivers tend to oversteep in certain areas and they tend to deposit in other locations. So it's very likely that some rivers may run the risk of actually making valleys a little more curved than they ordinarily would be over time. Glaciers tend to do the opposite. They like nice straight runs where they can deliver the ice very efficiently. Glaciers in a main or trunk valley typically erode more than tributary glaciers, creating hanging valleys. So this is in fact also a hanging valley. This is a valley that was formed by a glacier that was moving down, and below it was an even larger glacier. So this is, if we were down here at the lake, we'd look up and we'd see this glacier hanging up in the air above us. Really, really neat. And this implies that this whole area was glaciated all the way up to here for this to be able to feed in. Really cool. If you can think in 3 dimensions, you can understand this concept very clearly. As a matter of fact, here's a nice example of this. Here we see a main glacier moving through. We have a bunch of glaciers that are tributary glaciers that are feeding in. But because it erodes more deeply, and these are more shallowly, that when it's melted off, we see this deep glacial trough, but these hanging valleys are still sitting way up high. And in between them, of course, because we have valley glaciers between them, we get those sharp-edged valleys. And this is, of course, these sharp-edged hill ranges. And these sharp edges are called Aretes. That's what the name for this is. If you happen to have 3 or an intersection of 2 Aretes coming together, you usually form something called a horn, which is a really high point. The most famous of which being the Matterhorn in the Alpine mountains, in the Alps. Okay, so this is a typical progression of what these look like. Here's a hanging valley, a big U shape up here, and out of the bottom of it is a big waterfall going down into the main valley. And so what's at the bottom of some of these valleys? Well, we get Paternoster lakes, which form after parts of the bedrock filled with water. So this was a U-shaped valley here, or it still is actually. You can even see this is a lake system that people come and visit. And basically this glacier had retreated and it left a bunch of lakes behind. A cirque, which is a bowl-shaped depression, is typically found at the head of the glacial valley. So let's go back over here. The cirques are located up here. This is basically the top of if you want to call it the watershed. Here's another one. It's basically the catchment or the head catchment for the glacier. It's where the glacier originates. You can get an additional snowpack falling on top of it. You can get tributary glaciers, but this is where the head of the glacier is located. It's in a cirque. When 2 glaciers exist on opposite sides of a mountain, the dividing ridge erodes away, creating a gap called a col. This is something that I'm not going to spend a whole lot of time discussing, but it's an interesting feature nonetheless. This is usually what I like to show images of, are the Aretes and the horns. You know, so here we see a beautiful arete. You see this edge here that goes right up. Really jagged climbing, and of course over-steepened slopes, which are great for mountain climbing. Real adventure seekers like to go and climb these aretes. A horn is a pyramid-like peak, and it's formed basically where 2 aretes kind of come together. And this is the most famous of which is, of course, the Matterhorn in the Alps. That's what this picture is. All right, so it turns out that over time, you know, these glaciers try to work their way down towards the ocean. The funny thing about the ocean is that sea level tends to rise and fall. And so we find ancient glacial valleys, that have been drowned by the ocean over time, typically in Scandinavia. And so here we see a U-shaped valley, but it's underwater. And this one's actually underwater, and this one's underwater. These are all underwater, and this person is sitting up on top of an old arete. Here's another arete over here on this side. And looking at this, what is now a modern harbor. These are basically drowned glacial troughs, and they're called fjords. That's the word for it, fjord. All right. And so this is a system of fjords. They make for really excellent harbors. In ancient times, the Old Norse word for a fjord was the word vik. It's where we get the word Viking from. So anyway, you get the idea. This is a really cool place. All right, so the nature of glacial deposits is that they're really bizarre relative to everything we've talked about so far. Glacial deposits tend to be really poorly sorted. They tend to be really blocky. Here's a marker on the middle of this this glacial deposit, and here we have big boulders, and there's silts and sands and all kinds of stuff. It basically is a bunch of trash that is scoured out of the mountains by glaciers. And there are 2 ways that it gets deposited. One, directly deposited by the ice, right? The ice can bulldoze all that rock down into the valley and push it into a big pile, or pile it up onto the sides of the glacier. Another way is that it can, as it's melting, the sediments that are suspended within the glacier can be moved out when it melts, right? So sediments laid down by glacial meltwater are called stratified drift. Stratified implying that they formed layers, right? This is clearly not a stratified drift. This is, in fact, a type of glacial drift that is called a till. This is a glacial till. And so you get some really bizarre things happen in glacial deposits. So, in glacial till is deposited as glacial ice melts and drops its load of rock. So remember, we're talking about the way that Pluck was working earlier, that a glacier can come on, grab a boulder and move it, and then drop it later on when it melts. That's in fact exactly what this picture here is demonstrating. Is there was a boulder here, there's a glacier over the top of it, and then when the glacier melted, it dropped this boulder into this position right at the top of this situation. And this is called a glacial erratic. This is bizarre, right? Glacial erratics are boulders in the till or lying on the surface. Stratified drift, here we see nice layers in the soil horizon. We actually see some cobbles down below, probably from a meltwater braided stream. Sediment that is sorted by size and weight of the particles is called stratified drift. It's deposited by glacial meltwater rather than the glacier itself. In other words, the stratified drift can be deposited some distance away from the actual glacier position itself. All right, so we kind of have been building a case towards talking about the deposits themselves. These things called, these landforms that are made exclusively out of till are called moraines. So a moraine is a landform made of glacial till. Here is a glacier, here we see rocks piled up on the side. So a lateral moraine is one right here, is an accumulation of debris on the side of the glacial till. So here we see it right here. A medial moraine is created when two alpine glaciers converge. So this is kind of a cool picture because back here it implies that you can actually see one glacier here. There's another one that's actually coming in from around the hill over here. And they have their own lateral moraines on each side, but when they converge, those moraines actually converge. So we see this glacier is here, it's moving like this, and this one is over here, and in the middle, there's the lateral moraines of the two combined. Okay, and that's what this is showing right here. So these are called medial moraines. There's other kinds of till deposits that we need to talk about, and these are probably the most famous. Because a glacier is similar to a conveyor belt, regardless of the movement, sediments are constantly moved forward and dropped at the terminus, which means at the end, right? So it's constantly scouring stuff off the mountain and pushing it down. So an end moraine is an accumulation of debris that forms at the terminus of a glacier, usually from just the physical movement of the glacier bulldozing those rocks into that position. A ground moraine is a rock-strewn plain created as the glacier retreats. And so here we actually see a terminal moraine, and then down below it, there's that rock-strewn terrain that is left by a previous glacier ahead of this one. This image over here is of a relatively famous mountain in Hawaii. This is of Mauna Kea. There's a famous observatory up here on the top. But these zones right here, this is actually a moraine. This is a glacial till deposit located at the top. And there's an older moraine, there's little portions of it, there's an older moraine located down here also. So it implies that from time to time, Mauna Kea in the past has been glaciated, and those glaciers have moved down the mountain, at least down to this point here, about halfway down the mountain. Okay, currently there is no glacier on top. Really, really cool. Moraines can be very, very large. They're not always these little tiny things that just drop out of valleys. In this case, the ice sheets that extended these huge glaciers to the south created a whole series of islands off the coast of the United States in the New England area. Cape Cod, it turns out, is a giant moraine called the Harbor Hill Moraine. Okay? And that same moraine is also located in Long Island, and it's extended all the way along here. That implies that there was a huge ice sheet that came through and pushed all this material off. It scraped the land and piled up this huge amount of material from Cape Cod all the way to Long Island. There's another moraine that went even further. and made Nantucket Island Martha's Vineyard, and extend also into the Long Island area. And it's even just believed to be visible under the water. Okay, so absolutely incredible how important these things are. So Long Island is really just a giant series of moraines. Same thing with Martha's Vineyard and Nantucket. By the way, Cape Cod is kind of a combination of a moraine. So the moraine is the main part coming out, but there's actually a spit that comes up off the top, which gives it this distinctive hook appearance. Another cool feature are drumlins. So drumlins are just smooth, elongate, parallel hills composed of till and formed from ice sheets. And, these things aren't necessarily very large. Here's one right here. A lot of early archaeologists believe that these drumlins might have been ancient burial mounds used in by Native Americans. We've now come through and systematically through aerial photography been able to determine that they're almost all of glacial origin. There are in fact burial mounds, but they have distinctive shapes, and we can discover what those are pretty rapidly. These are drumlins right all through here. They're underneath the forest. We can see them, and we could tell pretty rapidly something about them. That the glacier moved either from one side to the other, but it didn't move in and out this direction. Same thing here. It didn't move in and out this direction. The glaciers either went from left to right or from right to left. So Bunker Hill is famous for the battle that is located, or the famous Revolutionary War battle that was fought by the United States against England during the early part of the Revolutionary War. All right. So here we see a beautiful glacier, actually two glaciers. There's a medial moraine. Here's a terminus. So we have a nice moraine piled up here. But that water comes through and it melts. And as it melts, it takes rocks and stuff with it, and it washes out. So glacial meltwater choked with sediment flows onto a flat surface, drops its load, builds up a broad ramp-like surface, and creates braided streams. So here we see beautiful braided streams. And we've talked about braided streams. If you don't recall, go back and review our surface water lecture on braided streams. And this is called an outwash plain. Right? This is a beautiful outwash plain. Valley trains are associated with mountain valleys, so this is something that is a little more local rather than something big and broad. Another really cool feature created by glaciers is these things right here. So these are ice contact deposits. The meltwater flows over within and at the base of motionless ice deposits. So you have a glacier and it's not moving. Right? You have an end moraine, you have a glacier, and in the middle of that glacier that's not moving, you have a hole in the ice. It's formed for whatever reason. Okay? And what can happen over time is as the glacier is melting and it begins to retreat, the water flows into that hole into the ice and it leaves the sediment there. And after a while, eventually the water all flushes out. The sediment stays there right where it was in that hole. And in the end, you wind up with a hill, right? In fact, this is what this hill is right here. It's a big pile of sediment that was in a hole in the glacier. This whole area being glaciated around it. And the end moraine, of course, would remain to this very day. Very, very cool. Very, very cool. This is an image out of the textbook that I like to use, showing how all these features might be distributed around a retreating glacier, right? And the reason why we care about a retreating glacier is because an advancing glacier would destroy all these things as it advanced and created an end moraine over here. Here's our outwash plains, here's our kettle lakes, which exist between the two, and our braided rivers and braided streams in the outwash plain. Really, really neat. Here's our drumlins. You get the idea. Cool, cool stuff. So other than carving the topography and making interesting hills and distributing boulders in bizarre ways, there are other effects that Ice Age glaciers have left us with. One of them being that when you pile a bunch of ice on land, it tends to put a lot of pressure. It actually bows down the crust of those areas. It downwarps the crust. And so what happens when the glacier melts? Well, the crust gradually moves back up. And so you wind up getting earthquakes in really bizarre areas where there's no faults because the earth is readjusting itself back outwards because the glaciers are no longer there putting downward mass or downward pressure on the rocks. They're also responsible largely for the sea level changes. During the last glacial maximum, sea level was 100 meters lower than at present level today, about 330 feet. And so when we look at this data, this would be our present day right here. And if we follow the graph down, this is thousands of years ago. At one point, at about 16 to 18,000 years, we can call it 17,000 if we want to be close. About 17,000 years ago, we hit the last glacial maximum, in which case the oceans were a full 330 feet or 100 meters lower than where they are currently. If the Antarctic ice sheet melted, sea level would rise a further 60 to 70 meters. So there's been a lot of difference that's happened here in terms of since the glacial maximum. Right? This image also shows during the last glacial maximum, the shoreline extended out onto the present day continental shelf. So, you know, currently the continental shelf, which is located offshore, was exposed. Okay? And in Europe, this was important because it allowed animals and people even ultimately to be able to move from mass to mass, such as from Europe into, or from continental Europe into England, whereas today they would have to take a boat to do so. It's also had the effect of changing drainages over time, right? So this would be an advance and retreat of the North American ice sheets changed the routes of rivers and modify the size and shape of many valleys. So the upper Mississippi drainage basin currently looks like this. You've got the Ohio, the Illinois, the Mississippi River here. The Red River drains to the north, and the Missouri River, of course, feeds into the Mississippi here. But in the past, we've been able to reconstruct old river systems prior to the Ice Age, and it looked very different. There were actually rivers where we currently have Great Lakes. The Red River was a dominant catchment basin, delivering material from the upper Missouri River, which currently now drains into the Mississippi. So over time, things change a lot. Okay, so ice ages are extremely important for determining the distribution of sediment, where things go, and of course where water ultimately is transported into the oceans. So the feeding of, or the growth of ice sheets on these large continents also fed very large alpine glaciers that could move across the land very long distances and create very large lakes. And these dams, these ice dams as they were called, can release very large volumes of water very quickly. You know, but here would be one of these lakes that covers most of central Canada and a portion of northern United States from, you know, just northwest of Lake Superior. This, you know, the province of Manitoba is not small, and there's a couple of remnants of this ancient Lake Winnipeg that extends all the way from Saskatchewan all the way down into Minnesota, and these little lakes are kind of what's left of it. And there's an example that's very famous in the United States called Lake Missoula. So this is Lake Missoula on a map, right? Lake Missoula was this lake. It wasn't nearly as large as the one up in Canada, but it was still very, very large. And essentially it was a series of rivers that got ice dammed, right? The glacier, a glacial lobe came down and blocked the drainage of the water. And eventually it built up a very, very large lake, much larger than present-day Lake Ontario. Very, very large lake. Okay, and what happened is at some point, the lake began to overflow that ice dam and began to cut down through it, or maybe catastrophically cut down through it. Some people think that maybe a volcano erupted and rapidly melted it. Whatever it was, this 2,000-foot high ice dam was breached very, very rapidly, and Lake Missoula drained very quickly. And today, when we look where Lake Missoula was and where that flood would have occurred, we see features like this. You know, this road giving us an example of what was going on. We see hills, little hill after hill. What kind of hill is these? What kind of hills are these? They're not drumlins. These are, in fact, the ripples from the flood. You know, these ripples have a wavelength of maybe 5 inches, maybe not even that, 3 inches. This is on a typical beach. But these are wavelengths of about 500 feet, right? These are the or the water ripples from the flow of the flood when Lake Missoula breached and went into the Pacific Ocean. Absolutely catastrophic event if it was to happen today. Okay, there are a lot of pluvial lakes. You know, the ice sheets have extended all over the place. These are pluvial lakes that would have existed during the Pliocene epoch, which is a period of time very recently, where we have very large lakes The Great Salt Lake, which is in Utah, is here, but it was part of a much larger lake called Lake Bonneville, which is now gone. Okay, so pluvial lakes are things that form, as a consequence of ice sheets and their relationship to temperature change over time. All right, so one of the things that we have kind of skirted around is what makes things get hotter or colder? What are the mechanisms? How do we know about this stuff? Well, let's look at some of the records that we have. So glaciers, we know by looking at the distribution of moraines and by looking at till deposits and things like this. Glaciers were once more extensive than they are today. So looking at glacial deposits and using the principle of uniformitarianism, we can go through and we can actually date these things. We haven't gotten to the lecture on how to date these things, but we will. And we find that there's a cycle where we go from a glacial period into an interglacial period to a glacial period to an interglacial period over time. And it seems to have a kind of a regular oscillation to it. Okay, so the northern hemisphere ice ages began between 2 and 3 million years ago, so it's nothing new here. This has been happening off and on for about 3 million years. And the Antarctic ice sheet formed at least 30 million years ago. So this has been kind of the rule for how Earth behaves. The recent warming trend that is discussed frequently in news outlets you should keep in mind that this is something that the Earth does frequently. Geologically, it goes up and it goes down. That doesn't mean I'm opining one way or the other on human-induced climate change, but just be aware that this is something that is normal for the Earth to go through, these oscillations. So the Quaternary Ice Age is not the only ice age in Earth's history in the last 3 million years, right? Antarctica has had ice for 30 million years. This is a tillite. It's a very ancient rock. You can actually see the polish on it from when a new glacier has gone over it. And this is a very, very ancient rock, much older than 30 million years. So there are different ways that we can cause ice ages, right? So we can make the simple argument of plate tectonics. Plate tectonics is usually where we have to look to all of our questions first, and then we can start asking more sophisticated questions from that basis. So continents shift and move through geologic time. And what does that do? That changes ocean circulation, right? The oceans, during the period of time of the dinosaurs, which is when Pangea existed, were one very large ocean. And the consequence of this is that you have totally different circulation patterns that existed at that time than exist now. And that has a dramatic effect on weather and therefore climate. Continents move towards or away from the pole. So if there's a continent that's sitting on a pole, it's more likely to accumulate ice and have an effect on sea level. If there isn't a continent on the pole, it can't accumulate ice, you just get sea ice, and you don't see those fluctuations. Climate change triggered by plate tectonics is extremely gradual and happens on a scale of millions of years. So the recent change, for example, in our own climate over time, over the last 100 years especially, that we've been monitoring this, where we could see the temperatures increasing, are probably not attributable to climate change. Not attributable to plate tectonics. There's just simply not enough plate tectonics occurring in that shorter period of time to justify the massive change. So in order to answer these questions, we have to answer these two issues. What causes the onset of the glacial conditions? What makes things get cold so that the glaciers begin to move? What caused the alteration of glacial and interglacial stages that have been documented for the Quaternary period? What causes that oscillation back and forth? So what makes things get cold and what makes it go back to interglacial and back and forth? And there's different ways, right? We talked about plate tectonics, but there are other factors, right? Changes in Earth's atmosphere over time. Volcanoes could have an effect. Perhaps a new forest that is very efficient at dealing with carbon dioxide might come into existence, or new species. Changes in the reflectivity of Earth's surface, right? The more snow you have on the Earth's surface, the more reflective the Earth's surface is, and therefore it actually drives a positive feedback and it gets cooler. So as the ice sheets get bigger, it drives it even more. And then, of course, in reverse, as the ice sheets retreat, it becomes less reflective and it warms even more. And of course, long-term solar fluctuations. The sun's radiance is not constant. It does fluctuate, and we do, as we do as geoscientists and astronomers keep a very close eye on solar fluctuations. Here we see a glacier that is melting. You can see the melt water is actually carving a nice little V-shaped canyon into the ice and draining into the ocean. And probably the best way that we can go about describing the glacial cycles, the back and forth, the up and down. You know, we're not really able to say definitively what causes the ice ages, but we are able to talk about what might cause the oscillations back and forth. So, for example, it turns out that the Earth in its orbit is not in a perfect circle. It's slightly elliptical. At one point, it's a little further than it is at another point. So that's important. The angle of Earth's axis changes over time. So we always take it for granted that the Earth's always spinning at the same angle, but it does in fact wobble a little bit. Okay, that's called obliquity. And then of course the wobbling itself of the Earth's axis over time. So not just the angle, but the axis itself. It's almost like a basketball spinning. As it's spinning, it starts to precess and rotate around. Those wobbles are called precession, and that's the reason why our North Star is changing all the time, right? During the time of the building of the pyramids, we had a very different North Star than we do today. Changes in climate over the past several 100,000 years are closely associated with variations in the geometry of Earth's orbit, right? So these factors all coming together at certain points could trigger an ice age or a glaciation event, and then undo it again in an interglacial period as well. Okay, there are other factors that are probably also involved in this cycle, and in fact, there's a new factor, that being human beings possibly being very, very much involved in the release of greenhouse gases that might be powering climate change in real terms in our lifetimes, as opposed to seeing it occur over a period of thousands of years. So anyways, I know it's a long lecture, a lot of information coming at you, so I'm going to go ahead and cut it off right there. If you have any questions, as always, give me a quick email. Until next time, have a good one.